Thanks Ralph, and hello everybody. Today we want to have a closer look at the airfoil inspection tools inside Control X. This toolset is part of the standard package, so no additional plugin is needed. You can find them right in the ribbon bar together with all the other built-in analysis tools. In addition to the simple 3D compare between the reference and the measured model here on the right side, with this set of tools you can extract dimensional information specific to airfoils, such as a 2D comparison between the reference and measured section through the blade, 2D measurements for airfoil specific features, and a 2D twist analysis to evaluate the blade profile without the deviation along the blade axis, the twist angle and the displacement along the section. In the airfoil analysis tool, besides a 2D comparison, the most common dimensions can be easily extracted as 2D measurements from each section, as shown in the images on the right. For easy reporting, the visibility of those measurements can be toggled on or off, and some parameters can be configured for different measurement principles. The 2D twist analysis tool performs a local best fit alignment, which can also be constrained to a maximum allowed transformation and rotation. This allows reporting the deviation between the reference section and the aligned measured section without the deviation along the whole airfoil, as well as the actual transformation and rotation of the measured section. So let's have a look at how to inspect an airfoil in Control X in today's live demonstration. I already imported the CAD model of the blade insert here, and also the scan data of this scanned airfoil. And I already did an alignment, in this case a datum alignment based on these planar faces in the root of the blade insert, because we want to inspect the upper airfoil part. The airfoil analysis is located in the Compare tab. Here we have two functions, the airfoil analysis and the 2D twist analysis. So in the airfoil analysis, first we need to specify a base plane, which can be any plane. It's like a constructed plane or a default plane like XYZ, or also a planar face in the CAD model, which I'm picking here. And we need an offset distance to define where we want to cut through the airfoil. In this case, I'm defining here by just pulling this arrow. I'm defining a cutting plane at plus 50 millimeter from the bottom face. And here you can already see this color is the deviation between the scan and the CAD section. Here we have some calculation options. You can define how the deviation is calculated, the shortest distance between scan and CAD, or along the normal of the CAD file, or custom. And here we can define the local coordinate system, where the origin is, where the x-axis direction is. So if I, for example, if I have a look at this, then I can define my x-axis using those buttons, flip x-axis and flip viewing direction. I can define the x-axis for this section view. In the next stage we go into the section view, and now we have a digital representation of the blade section. Here the solid black line is the CAD section and the colored line is the scanned section with the displacement vectors in between, also called whiskers. So those whiskers can be multiplied to magnify the deviation in case the deviation is very small, so we can see it. And the whisker display ratio we can reduce to unclutter the view in case there are many sampling points, so we can reduce the number of sampling points. And here we have the color bar option. This is directly influencing the color bar. So I can here enter a maximum or minimum range for the color bar. At the moment we have 1 millimeter here, and I can increase that to 2 millimeter. And here I can give a specific tolerance. For example, instead of 0.1 we can put 0.5, so that the whole blade deviation is blade section deviation is inside the tolerance. In the third stage, we need to define where the leading edge is pointing. So we have a positive x-axis here, and we have the leading edge located in the positive x-axis direction. So we can select here this plus x. Next, we can check which dimensions we want to evaluate. So we have, for example, the leading edge radius and the leading edge thickness here, and the trailing edge thickness and trailing edge radius as well. And we have a maximum thickness around here. And let's put another one. This is the chord length, for example, around here. And all those values have a tolerance. So we can also edit the tolerances. For example, for the maximum thickness, it's +1, and for the leading edge thickness, let's put 0.5. So we can click in here and edit this value to 0.5. So it's directly represented 0.5 as well. And for the radius, we can put 0.2 as well here, 0.2, and this is directly updated. So when I move my mouse over this annotation, I can also see the features which are created automatically, and the dependency. So for this dimension, it is the circle here and the circle here, and this is the tangent or the chamber line intersection, depending on the option. And we can also see the dependency elements in this airfoil structure under the model manager. So this is the airfoil analysis, and we have the 2D twist analysis. It's basically the same as a 2D analysis, just with a little twist. In this case, we can select the plane, the base plane as well. And I'm pulling up the section to 100 millimeter this time. As well, we can check the viewing direction so that we have the same. Disable this airfoil so that we have the same viewing direction. Also, our leading edge is in the positive x-axis direction. Then we go into the second step, and also the display option and the color bar option is the same in this case. But what we can see here, we have now a very small deviation only, because if I go back one step, I can see that there is a bigger deviation. And the 2D twist analysis basically performs a best fit alignment of this section to get rid of the overall deviation of the blade and only evaluate the deviation of the blade profile. And the transformation that actually happens during this best fit can be seen here in the twist movement section of the property panel. Here you can see the twist trans X and twist trans Y and twist rotation in millimeter and in degree. As well, there is a matrix which can be exported, but this is the interesting human readable values to report. Also, we have the possibility to define how the transformation happens. In this case, it happens by a rotation around the global origin, around the section origin, which is stacked directly above the global origin in the CAD file. But we can also choose to use the centroid point. And we can also choose different primary axes and different secondary axes. So depending on the needs, we can change that. Also, we can define a constraint for the movement. In this case, without any constraint, the best fit is unlimited. So it's trying to minimize the deviation. And if I enter a value here, which is smaller than the total deviation like 0.2, then the best fit is limited in this direction and stops at 0.2 maximum displacement from the original position. Same thing is with Y and with the rotation. And yeah, that is basically it for the 2D twist analysis. This can be also reported. So we can go to the report manager and just for those two features and generate a report. So here we have the airfoil analysis report with the picture, and here with the data. And here we have our 2D twist analysis as a picture and also with the data. This is the twist transform X, Y, and the twist rotation. This can of course be configured to any needs. So it's kind of PowerPoint style or Word style report designer. And since this is parametrically stored in this model manager, it's also repeatable by just replacing the measured data. There will be completely recalculated and the report will be regenerated. Also, we can import, instead of CAD file, we can import another scan, and the same thing is also possible to do with scan against scan comparison, and this is also parametric and repeatable. That concludes the live demo of today, and thank you, and back to you, Rolf.